80 milliseconds behind reality. What you experience as the present is not quite the present. The brain takes time to process incoming information. Light reaches the eye in microseconds. The signal then travels through the optic nerve, gets sorted in the visual cortex, gets matched against memory and context, and only then becomes a conscious perception. By the time you experience the world has already moved on. The lag is roughly 80 milliseconds for vision and somewhat less for sound. This delay matters in everyday life. When you swing a bat at a moving ball, the ball you see is where it was, not where it currently is. To hit it, the brain unconsciously predicts where the ball will be 80 milliseconds in the future and aims the swing there. Athletes who are better at this prediction are better at sports. The seeing has nothing to do with the speed of the swing. The predicting does. The brain hides the lag from you. Through a kind of internal forward modeling, your perceived present is pushed ahead to approximate real time. You feel like you are seeing the present, even though your brain is showing you a slightly delayed reconstruction projected forward. The illusion is so seamless that most people never notice. Optical experiments with rapidly moving lights can briefly break the illusion and show the underlying lag, but only in laboratory conditions. The implication is that your conscious experience is, in a strict sense, a reconstruction. You are never seeing what is happening right now. You are seeing a guess about what is probably happening right now, based on a record that arrived a fraction of a second ago. The world has moved on while your brain was still building the picture. The version you call reality is, on close inspection, a careful estimate. Particles through walls. In classical physics, a ball thrown at a wall bounces off. If the wall is strong enough and the ball is too slow, no amount of trying will get the ball through. The wall is a barrier. Either the projectile has enough energy, or it does not. In quantum mechanics, the rules are different. A particle with too little classical energy to cross a barrier sometimes does it anyway, by passing directly through. The effect is called quantum tunneling. Tunneling is not a thought experiment. It is one of the foundational processes of modern physics. Electrons in a hydrogen bond tunnel between atoms regularly. Protons in the cores of stars, including the Sun, tunnel through their mutual electrical repulsion to fuse into helium. Without that tunneling, fusion would happen so slowly that no star could shine. The sunlight reaching your skin came from particles that, by strict classical rules, should not have been able to touch each other. Modern electronics depend on the same effect. Flash memory, the storage in nearly every modern phone and computer, operates by electrons tunneling through thin insulating layers to write and erase data. Tunnel diodes work the same way. Scanning tunneling microscopes, which image individual atoms, measure the small current of electrons tunneling between a sharp tip and a surface. Whole industries are built on particles passing through what classical physics calls a closed door. The strangeness does not stop at the wall. The probability of passing through depends on the thickness and height of the barrier, but never goes to zero. Even a wall a meter thick has, in principle, some vanishingly small probability of being penetrated by a particle. Sit at your desk long enough, and the air in your lungs has a non-zero chance of tunneling through your skin. The chance is so small you never see it. The rule, however, is not zero. Observer changes reality. The double-slit experiment is one of the most studied demonstrations in physics. A beam of light or a stream of single particles is fired at a barrier with two narrow slits cut into it. Behind the barrier is a detector that records where the particles arrive. When the experimenter does not check which slit each particle goes through, the pattern that builds up on the detector is one of overlapping bands, the classic interference pattern that suggests waves passing through both slits at once. When the experimenter adds a detector to determine which slit each particle goes through, the pattern changes. The interference vanishes. The particles now arrive in two clumps, one behind each slit, like ordinary projectiles. The act of measuring which path the particle took has changed the behavior of the particle. The wave-like pattern only appears when no measurement is being made. The effect is not a quirk of equipment. It has been performed with photons, electrons, atoms, and even small molecules. In every case, the same result. Acquiring path information destroys the interference. Removing path information restores it. The behavior of the system depends on whether or not someone is watching, in the strict sense that information about the path exists somewhere in the world. The interpretation is still debated. The most widely accepted view in working physics is that the measurement is not a passive observation, but an interaction that disturbs the quantum state. Whatever the philosophical reading, the experimental fact is unambiguous. Reality at the quantum scale behaves differently depending on whether or not it is being observed. The world, in some careful technical sense, does not simply sit there waiting to be seen. Your atoms replaced, the human body is in continuous chemical exchange with its environment. Cells die and are replaced. Atoms come in through food, water, and air, and leave through breath, sweat, and waste. Over time, the matter making up your body turns over almost entirely. The exact rate varies by tissue. Cells in the gut lining are replaced every few days. Red blood cells last about 4 months. Skeletal muscle turns over in years. Bone takes about a decade for complete replacement. The result is that almost none of the atoms that made up your body 10 years ago are still in your body today. The protein in your muscles, the calcium in your bones, the lipids in your brain are all newer arrivals. The body you carry around is, materially speaking, a slow-flowing river rather than a solid object. The pattern persists. The matter circulates. A few exceptions exist. Certain neurons in the cerebral cortex appear to last for the entire life of the person who carries them, with limited replacement. The lens of the eye, which has no blood supply after fetal development, keeps cells from the very early life of the body. Some tooth enamel is laid down once and never replaced. These are small islands of stability in an otherwise constantly renewed system. The implication is unsettling. The thing you call yourself, the body that walks around and sees the world, is not the body you had a decade ago in any straightforward sense. The atoms have all been swapped out, like a ship replaced plank by plank over many years. What remains is the pattern, the arrangement of information and structure that the body maintains as new matter passes through. You are, in this strict sense, an organized flow rather than a fixed thing. Time runs differently. Einstein's general relativity predicts that time runs at slightly different rates at different gravitational potentials. The closer you are to a massive body like the Earth, the slower time passes. The effect is small at human scales but real. Clocks at the bottom of a tall building tick measurably slower than identical clocks at the top. This is not a theoretical curiosity. The global positioning system depends on accounting for the effect. GPS satellites orbit thousands of kilometers above the Earth, where gravity is weaker and time runs slightly faster than on the ground. If the system did not correct for the difference, GPS positions would drift by kilometers per day. The clocks on board the satellites are programmed to tick at a slightly different rate, so that, By the time their signals reach ground users, they match the ground rate of time. Inside a single human body, the effect also exists, although it is unimaginably small. Your head is, on average, about 1.5 meters farther from the Earth's center than your feet. Time at your head therefore runs marginally faster than time at your feet. The difference is around 1 part in 10 to the 16th. Over a full human lifetime, your head will have aged by something like a few hundred billionths of a second more than your feet. The numbers are absurd in human terms. The principle is not. Time is not a single universal flow. It runs at different rates depending on where you are in a gravitational field. Astronauts on the International Space Station, after long missions, return slightly younger than they would have been on the ground, because the orbital combination of speed and altitude shifts their clock relative to ours. Your body is, very slightly, a clock that goes at different speeds at different ends. Invisible blind spot. Each of your eyes has a small region of the retina with no light-sensitive cells. The location is where the optic nerve leaves the eyeball to carry visual information to the brain. Because the nerve fibers exit through this spot, there is no room for the rods and cones that detect light. Anything whose image falls on this patch of the retina is, for that eye, invisible. You do not normally notice the blind spot. The two eyes compensate for each other, since each eye sees what falls in the other's blind region. Even with one eye closed, your brain quietly hides the gap. Instead of leaving a black patch in your visual field, the brain fills it in with the surrounding colors, textures, and patterns. The reconstruction is so seamless that you can stare at a complex scene with one eye closed and never notice the missing piece. You can demonstrate the blind spot with a simple test. Close one eye, fix your open eye on a small target, and slowly move a second small mark away from the target at the same distance from your face. At a particular position, around 15 degrees off the line of sight, the second mark vanishes. It is still there. The brain is simply leaving the mark out, painting over its location with the surrounding pattern. The implication generalizes. The world you see is not a direct projection of what is in front of you. It is an actively constructed scene, with gaps quietly papered over and missing pieces invented to maintain a continuous picture. Most of the time, the inventions match reality closely enough to be useful. The fact that the construction exists at all is something most people never directly experience. Quantum entanglement. Quantum mechanics allows two particles to become entangled. Their properties are linked in a way that classical physics has no analog for. A measurement on one particle instantaneously determines the corresponding property of the other, regardless of how far apart they are. The link is not a hidden signal traveling between them. It is a single quantum state shared by the two particles, which only resolves into definite values when one of them is measured. Einstein called the effect spooky action at a distance and refused to accept it as fundamental. He suspected that the particles had simply been carrying matched hidden variables since their separation, like two cards drawn from a sorted deck. In the 1960s, the physicist John Bell showed that this view could be tested. If the particles carried hidden variables, the correlations between measurements at different angles would obey a specific mathematical limit. If they were truly entangled, the correlations would exceed it. Experiments since the 1970s have consistently violated Bell's limit. The particles really are entangled in the strong sense. Recent experiments, including the careful work that won the 2022 Nobel Prize in Physics, have closed nearly every loophole in the test. The conclusion is now experimentally secure. Quantum entanglement is a real feature of the world. The link cannot be used to send a faster-than-light signal, because the result of any individual measurement is random. Only when the two distant observers compare notes afterward does the correlation become visible. Yet the correlation itself is stronger than anything classical physics permits. Two particles, separated by any distance, can share a quantum state that the universe respects as one thing. Hot water freezes. In 1963, a Tanzanian secondary school student named Erasto Mpemba noticed that the hot ice cream mixture he was preparing froze faster than the cold mixture his classmates had made. He asked his teacher about it and was told the result was impossible. Mpemba kept asking. Eventually, a visiting professor took the question seriously and started a series of experiments that confirmed the strange observation. Under some conditions, hot water freezes faster than cold water. The effect is now known as the Mpemba effect. It is real, repeatable, and surprisingly hard to explain. Various mechanisms have been proposed. Evaporation removes some of the hot water before freezing begins, reducing the volume that needs to cool. Convection in hot water is stronger, mixing the temperature more uniformly. Dissolved gases come out of solution in hot water, changing the freezing behavior. The container holding the hot water can lose heat more efficiently through its surroundings. No single explanation has accounted for all the experimental observations. Different experiments seem to involve different combinations of these effects, depending on how the water is held, what is added to it, and how the cooling is done. Recent work has even questioned whether the effect appears reliably enough to be called a real phenomenon at all. The debate has produced a steady stream of papers without a final answer. The deeper lesson is that ordinary water, which most people consider simple, has unexpected layers. The substance freezes, boils, and dissolves under conditions every chemistry student studies. Yet a simple question about the path to freezing has resisted clean explanation for 60 years. The everyday materials of life are full of small anomalies. Some of them resist the most careful attempts to settle them. Banach-Tarski paradox. In 1924, two Polish mathematicians, Stefan Banach and Alfred Tarski, proved a theorem so strange that it sounds like a hoax. Take a solid ball. Mathematically, decompose it into a finite number of pieces, just 5 in the standard version. Move and rotate those pieces without stretching or distorting them. Reassemble them. The result is 2 identical balls, each the same size as the original. Volume has, by all appearances, been created from nothing. The theorem is not a trick. It is a rigorously proven mathematical result. The pieces involved, however, are not solids in any ordinary sense. They are infinitely complex sets of points, with no continuous surface and no well-defined volume. Pieces of this kind exist in mathematics, but they cannot be cut out of a real ball with any physical tool. Each piece is a fractured cloud of mathematical points, and the rearrangement is a careful choreography of those clouds. What the theorem reveals is that the concept of volume, when stretched to its limits, does not behave the way intuition expects. Most subsets of 3-dimensional space are not measurable in the standard sense. They have no volume to add or subtract. By assembling carefully chosen unmeasurable pieces, you can apparently double a sphere without changing the total volume, because the very notion of total volume breaks down at the intermediate stages. The theorem requires a controversial assumption called the axiom of choice. Most mathematicians accept the axiom because rejecting it makes much of standard mathematics impossible. Some philosophers and a minority of mathematicians find the consequences unacceptable. Either way, the theorem stands. A ball can, by precise mathematical rules, be cut into pieces and rearranged into 2 balls. The cut is not physical. The rearrangement is exact. Quantum vacuum. Empty space is not empty. According to quantum field theory, every region of the vacuum is filled with what are called virtual particles. These particles flicker into existence in matched pairs, last for a tiny fraction of a second, and annihilate one another before they can be directly detected. The Heisenberg uncertainty principle allows brief violations of energy conservation, as long as the energy is paid back quickly enough. The particles are not just a theoretical artifact, they produce measurable effects. The Casimir effect, predicted in 1948 and first measured in 1997, shows that two uncharged conducting plates placed very close together attract one another. The cause is the imbalance between virtual particles allowed inside the narrow gap and those allowed outside. The reality of the effect and the precision of its measurement mean the virtual particles in empty space are doing real work. The Lamb shift in atomic spectra, the magnetic moment of the electron, and the behavior of various scattering experiments all match calculations that assume the vacuum is full of these flickering particles. The most precise predictions in all of physics, accurate to better than 1 part in a trillion, depend on summing contributions from a sea of virtual particles. Without them, the numbers do not match the experiments. The implication is that the vacuum is not the absence of matter. It is a dense and dynamic medium, with energy and structure, constantly producing and absorbing particles too brief to capture. The visible world of matter sits inside that medium. The empty space around you, the gap between your eyelashes, the space inside your atoms, all contains the same boil of virtual particles. There is, in this strict sense, no such thing as nothing. Light experiences timelessness. The speed of light is an absolute limit in special relativity. No information, no signal, no object with mass can travel faster than light through a vacuum. The closer an object approaches that limit, the more its experience of time and space distorts. Time slows down, lengths contract. At the limit itself, the equations of relativity produce a striking result. Time, in the strict mathematical sense, does not pass at all. From the point of view of a photon, the particle of light itself, the entire journey across the universe happens in zero time. The photon is emitted by a star, travels for what an outside observer would call billions of years, and arrives at a telescope on Earth in what the photon would experience as no time at all. For the photon, no clock ticks between departure and arrival. The trip is, in a strict relativistic sense, instantaneous. This is not a metaphor or an interpretive flourish. The relativistic equations are unambiguous. The proper time experienced by an object moving at the speed of light is exactly zero. The light from the most distant galaxy, having travelled across over 13 billion years of our time, has, by its own accounting, experienced no duration. It has been everywhere at once. The conclusion is among the strangest consequences of relativity. Light, the carrier of every astronomical observation, has no notion of past or future. The history of the universe, written across billions of years, is for every photon a single timeless event. The clock of the photon never starts. The journey is, by every formal measure, an instant. From the inside of light, the universe is 1 moment long. Birthday paradox. In a room of 23 randomly chosen people, the probability that at least 2 of them share a birthday is more than 50%. The result is often called the birthday paradox, not because it contradicts logic, but because it surprises almost everyone who hears it for the first time. People expect the number to be much larger, closer to 100 or 200. The actual threshold is much smaller. The reason is the difference between pairs and individuals. With 23 people, the number of possible pairs is 253. Each pair has a small chance, around 1 in 365, of sharing a birthday. Add up all those small chances, and the probability of at least one match grows quickly. By 23 people, the cumulative probability crosses 50%. By 70 people, it exceeds 99.9%. The pattern matters in cryptography. Many cryptographic algorithms rely on the difficulty of finding two different inputs that produce the same output. The birthday paradox shows that, in any large enough collection, such collisions are likely to exist long before one might expect. The square root of the size of the output space sets the practical threshold. Designers of secure systems use this insight to choose key sizes that resist collisions. The takeaway is that human intuition about probability is poor in this region. People reliably underestimate how often coincidences occur in moderately sized groups. A classroom, a sports team, even a dinner party usually contains more shared birthdays, names, or other small overlaps than people expect. The world contains more matches than intuition predicts. The matches do not require any deep cause. They follow from the simple counting of pairs. Superluminal expansion. The universe is expanding. The discovery in the 1920s, made by Edwin Hubble and others, showed that distant galaxies are moving away from us, and the more distant they are, the faster they recede. Subsequent measurements have refined the picture into one of an expanding fabric of space itself, not just galaxies flying apart through pre-existing space, but the space between galaxies stretching. The stretching is faster than light. This sounds, on its face, like a violation of relativity, which sets light speed as the cosmic speed limit. The contradiction is only apparent. Relativity forbids any object from moving through space faster than light, locally. The expansion of space itself is a different process. Two galaxies sitting still in their own neighborhoods can still find the space between them growing at a rate that, totaled over enough distance, exceeds light speed. The consequence is that some galaxies are receding from us faster than light. Their light, once emitted in our direction, never catches up to the still expanding space and never reaches us. These galaxies are, in every practical sense, lost to us. The boundary of objects still visible is called the cosmological horizon. Beyond it lies a universe we can never observe. The horizon is not a fixed wall in space. It is the boundary set by the expansion rate. New galaxies cross it constantly, leaving the visible universe. Modern dark energy measurements suggest the expansion is accelerating, so the horizon is shrinking in terms of how much of the cosmos remains observable. Over the next few 100 billion years, almost every galaxy outside our local cluster will leave the horizon for good. Most of the universe will, in time, become invisible to anyone looking from here. Climbing liquid. Helium, the second lightest element, has a strange property when cooled to temperatures near absolute zero. Below about 2.2 degrees above absolute zero, liquid helium undergoes a transition into a state called a superfluid. The superfluid phase behaves like no ordinary liquid. It flows with no viscosity at all. It can pass through cracks far too small for any ordinary fluid. It conducts heat enormously well, and most strangely, it climbs walls. The climbing effect is called the Rollin film. A superfluid placed in an open container does not stay in the container. A thin layer of liquid creeps up the walls, over the rim, and runs down the outside. The film is roughly 30 atoms thick, driven by van der Waals forces between the helium and the wall. Because there is no viscosity, no friction at all resists the flow. the liquid happily climbs out and drains itself onto any surface below. The behavior is direct evidence of quantum mechanics operating at a macroscopic scale. In a superfluid, a large fraction of the helium atoms have entered the same quantum ground state, behaving collectively as a single coherent wave function. The classical concepts of friction, viscosity, and surface tension that govern ordinary fluids no longer apply. The fluid moves with a unity that ordinary matter cannot achieve. The strangeness extends further. A superfluid in a rotating container forms an array of microscopic quantum vortices, each carrying a fixed quantum of angular momentum. Sound waves in the fluid can propagate as two distinct types, called first sound and second sound, each traveling at a different speed. A vessel full of superfluid helium is a quiet container holding a state of matter that, in nearly every visible respect, breaks the rules of everyday liquids. Cosmic afterglow. About 13,800,000,000 years ago, the universe was a hot, dense plasma of ions and free electrons. Light could not travel far through this plasma. After roughly 380,000 years of expansion and cooling, the temperature dropped enough for electrons to combine with nuclei into neutral atoms. The universe became transparent. Light that had been scattering through the plasma was suddenly released, free to travel. That released light is still here. It has been stretched by the expansion of the universe over 13 billion years until its wavelength is now in the microwave range. Every point in the sky, in every direction, glows faintly with this radiation. It is called the cosmic microwave background. A small piece of the static on an old analog television, when tuned between channels, is microwave radiation from the very early universe, arriving directly in your living room. The radiation carries information. Its average temperature is around 2.7 degrees above absolute zero, with tiny variations of 1 part in 100,000. Those small variations record the density fluctuations of the universe at the moment the light was released. From the pattern, cosmologists can reconstruct the age, geometry, and composition of the universe with surprising precision. The cosmic microwave background is the most carefully measured photograph in the history of science. The implication is that the early universe is not hidden in time. It is still visible in the form of the oldest light any observer can see. Every direction you turn in any part of the sky, the same faint microwave glow arrives. It is the residual light from the birth of the cosmos, drifting out of the deep past in real time, washing over every telescope and every television antenna on Earth. Why chairs hold. When you sit on a chair, you do not fall through it. The surfaces of you and the chair touch and stop, and you remain on top of the structure. The reason might seem obvious, but the underlying physics is not. Atoms are mostly empty space. The volume occupied by a nucleus and its electron cloud is mostly vacuum at the quantum scale. By volume, you and the chair are nearly all empty, yet the empty parts do not pass through each other. The reason is the Pauli exclusion principle. Electrons are fermions, a class of particles that obey a strict rule. No two identical fermions can occupy the same quantum state at the same time. When you press your hand on a tabletop, the electron clouds of the atoms in your hand and the tabletop are pushed close together. The exclusion principle prevents the electrons from overlapping into the same states. The cost in energy of trying to force them into shared states becomes enormous, and the atoms repel one another strongly. The repulsion is what we experience as solidity. It is not electromagnetic repulsion in the simple sense, although electric forces do play a role. The dominant effect is purely quantum, a consequence of the rule that no two electrons can sit in the same place doing the same thing. This is also why white dwarf stars, where atoms have been crushed by gravity, remain stable. The electrons cannot be packed any tighter without violating the exclusion principle. The implication is that the everyday experience of solid objects is, at its core, a quantum mechanical effect. The chair holds you up because of a rule about identical fermions. Without the Pauli principle, ordinary matter would collapse. The hardness of your floor, the impenetrability of your hand, the sense that things have surfaces, all rest on a quantum rule about how electrons share states. Unprovable truths. In 1931, the Austrian logician Kurt Gödel published a result that reshaped the foundations of mathematics. He proved that any consistent formal system, rich enough to express ordinary arithmetic, contains true statements that cannot be proved within the system itself. The result is known as Gödel's first incompleteness theorem. Mathematics, as a formal system, contains truths it cannot reach by its own rules. The proof works by constructing a specific self-referential statement. The statement essentially says of itself that it cannot be proved. If the statement could be proved, then it would be false, and the system would be inconsistent. If it cannot be proved, then it is true. Either the system is broken, or there is a true statement it cannot reach. For any consistent system, the conclusion is the second one. Truth, in mathematics, outruns provability. The implication shocked the early 20th century mathematical community. David Hilbert, one of the most influential mathematicians of the time, had proposed an ambitious program to put all of mathematics on a complete and self-verifying foundation. Gödel's theorem proved that no such foundation can exist. Any reasonable system of mathematics either misses some truths or proves contradictory ones. There is no clean middle ground. A second incompleteness theorem followed quickly. Gödel showed that no consistent formal system can prove its own consistency. Mathematics, in some strict sense, cannot fully understand itself. The result is not a skeptical attack on mathematics. Working mathematicians continue to prove theorems and verify results, mostly without ever encountering Gödel's limit directly. But the limit is there. Somewhere in the landscape of true statements about numbers, there are facts that no proof will ever reach. Invisible eye movements. Your eyes do not move smoothly across a scene. They jerk rapidly from one fixation point to the next. The fast jumps are called saccades. Between fixations, the eyes move at hundreds of degrees per second. The image on the retina during a saccade is a blur, like a camera being whipped back and forth. By every reasonable expectation, your visual world should look like a smeared chaos most of the time. It does not. You experience a stable, sharp image of the world, with no perception of motion blur between fixations. The brain achieves this through a process called saccadic suppression. During the saccade itself, the brain actively suppresses visual input, ignoring the blur and inserting an interpolated image to fill the gap. You see the scene before the eye moves, then the scene after, with no record of the chaos in between. The mechanism extends to time. Brief events that occur during a saccade are often experienced as lasting longer than they really did. When you glance at a clock and the second hand seems to pause briefly before resuming, you are experiencing a related effect called chronostasis. The brain back fills the perceptual time you missed during the saccade. The effect demonstrates how much active editing the brain does to produce a coherent visual experience. Saccades happen several times per second during normal vision. The total time your eyes are in fast motion adds up to a significant fraction of every day. None of that time produces a perceived blur. The brain quietly skips over the blurred frames and stitches the sharp ones together, leaving you with a smooth picture that, in raw retinal terms, looks nothing like what you see. Quantum Zeno, a quantum system, left to itself, evolves through its possible states. An unstable particle, for example, decays with a certain probability per unit time. A measurement of the system, however, collapses its quantum state to a definite outcome. If a quantum system is observed continuously, with repeated measurements coming so frequently that the system has no time to evolve between them, the system can be effectively frozen in place. The effect is called the quantum Zeno effect. The name comes from the ancient Greek philosopher Zeno of Elea, who argued that motion is impossible because an arrow at any single instant is at rest. In the quantum case, the analogy holds. Watching closely enough prevents the system from moving. The mathematics was worked out in the 1970s by Baidyanath Misra and George Sudarshan, and the effect has since been confirmed experimentally with trapped ions, beryllium atoms, and other quantum systems. The mechanism is straightforward in the formal theory. A quantum state evolves over time, gradually developing a small probability of being found in a different state. A measurement collapses the wave function back to its original state with high probability. If the measurements come quickly enough, the system is repeatedly reset before significant evolution can occur. The cumulative effect is to keep the system pinned in its initial configuration. The implication challenges naive intuitions about observation. In classical physics, observing a system does not change its behavior. In quantum mechanics, the act of observing is itself a physical interaction that affects the system's evolution. A particle being watched too carefully cannot decay. A nuclear transition being measured continuously cannot proceed. The world really does behave differently when it is being watched, in this very strict and experimentally confirmed sense. Larger infinities. In the late 19th century, the German mathematician Georg Cantor showed that not all infinities are equal. Some are genuinely larger than others. The argument is now called Cantor's diagonal argument and is taught in introductory courses on mathematical logic. Despite its simplicity, the result was so radical that Cantor's contemporaries dismissed it as nonsense, and Cantor himself suffered breakdowns over the resistance to his work. The argument runs as follows. Suppose you list every real number between 0 and 1 in some order. Write each number as an infinite decimal expansion. Cantor showed that you can always construct a new real number that is not in your list by choosing each digit differently from the corresponding digit on the list's diagonal. The newly constructed number cannot be in the list because it differs from every list entry in at least one place. The set of real numbers is therefore strictly larger than the set of natural numbers, even though both sets are infinite. The result establishes a hierarchy of infinities. The smallest infinity, called Aleph 0, is the size of the natural numbers. The size of the real numbers is strictly larger. Cantor showed that, from any infinite set, you can construct a larger one by taking the set of all its subsets. The hierarchy goes on without end, with infinities of larger and larger size, each strictly bigger than the last. The conclusion is one of the most counterintuitive results in mathematics. Infinity is not a single thing. It is a whole landscape of different sizes, each provably larger than the previous one. The fact that some infinities are bigger than others is now a foundational part of mathematics. The path from intuitive numerals to this hierarchy is short. The implications stretch into nearly every part of modern mathematics. Delayed choice. In 1978, the physicist John Archibald Wheeler proposed a variation of the double-slit experiment that pushed quantum mechanics into stranger territory. The delayed choice experiment asks what happens if the decision to measure which slit a particle goes through is made after the particle has already passed through the slits. In the standard reading, the particle should have already either acted as a wave or a particle by the time the choice is made. The future cannot reach backward into the past. Actual experiments performed since the early 2000s confirm that the future does, in a careful technical sense, influence the past. If the apparatus records which path information about each particle, the resulting pattern is the two-clump particle distribution. If the apparatus erases the information after the particle has passed through, the wave-like interference pattern reappears. The choice of measurement, made after the particle's transit, determines what the particle did during the transit. The result is not a violation of causality. No information can be sent backward in time. The pattern only becomes visible when the observers compare their records after the experiment. But the correlation between the late choice and the earlier behavior is unambiguous in the data. The particle does not have a definite history independent of the eventual measurement. The history is, in some strict mathematical sense, only fixed when the recording is complete. The interpretation continues to be debated. Some physicists argue that quantum mechanics simply does not allow particles to have well-defined classical histories, and the experiment exposes that fact. Others see a stronger form of retrocausality at work. Either way, the experimental data is clear. A choice made now can determine the pattern set by particles that already pass through the apparatus. Glass flows. Glass occupies an awkward category between liquid and solid. It does not flow like an ordinary liquid. It holds its shape, takes a polish, and shatters like a brittle solid. But it does not have the regular atomic lattice that characterizes true crystalline solids. The molecules in glass are arranged in a disordered way, more like a frozen liquid than a crystal. By the strict structural definition used in solid-state physics, glass is an amorphous solid, sometimes called a non-equilibrium glass former. The behavior follows from how glass is made. When silica or another glass-forming material is cooled from a liquid melt, the molecules begin to slow. If cooled slowly enough, they arrange themselves into a regular crystal. If cooled quickly, they freeze in the disordered arrangement they had in the liquid state before they can crystallize. The result is a substance with a liquid structure but a solid's mechanical behavior. A persistent legend claims that medieval cathedral windows are thicker at the bottom because glass flows slowly over centuries. The legend is wrong. The thickness variation is an artifact of how the panes were manufactured. Old glass was made by spinning or rolling, producing panes that were thicker on one side. Glaziers traditionally installed the thicker edge at the bottom for stability. Modern measurements show that glass at room temperature does not flow on any human timescale. That said, glass at warmer temperatures does flow gradually. At its glass transition temperature, the substance becomes a true liquid. The intermediate region between liquid and solid is genuinely strange and an active area of research. Whether glass should be called a slow liquid, a special kind of solid, or something else entirely, is not a settled question. The substance in your windows is, by every careful measure, sitting on the edge between two states of matter that nature does not cleanly separate. Quantum bird navigation. Many migratory birds find their way across continents using the Earth's magnetic field as a compass. The mechanism by which they detect the field is not the simple magnetized needle of an old-fashioned compass. Modern research suggests that the birds use a quantum mechanical process involving entangled electron pairs in a protein called cryptochrome located in the retina. When a photon of blue light hits the cryptochrome protein, it produces a pair of unpaired electrons whose spins are quantum mechanically entangled. The behavior of the pair, as it evolves through different spin states, depends on the local magnetic field. Subtle changes in the field shift the chemistry of the reaction, producing different downstream products at slightly different rates. The bird's nervous system, in some still poorly understood way, reads this chemistry as a direction. The implication is that birds may literally see the Earth's magnetic field as a visual overlay, perhaps as a faint color or pattern superimposed on the rest of their vision. Experiments have shown that birds become disoriented when the cryptochrome system is disrupted, and that exposure to weak oscillating magnetic fields at specific frequencies, predicted by the quantum mechanical model, disrupts their navigation. The biology lines up with the theory. This is one of the clearest known examples of quantum mechanics operating in a warm biological system at room temperature. Most quantum effects require cold, isolated conditions to remain coherent. Cryptochrome appears to evade this limit using some specialized molecular structure that protects the spin states long enough for the magnetic field to matter. Photosynthesis and some smell receptors may use similar tricks. The strict line between classical biology and quantum physics, once thought to be sharp, has turned out to be more porous than expected. Human microbiome. The human body is colonized by an enormous community of microorganisms. Bacteria, viruses, fungi, and archaea live on the skin, in the mouth, in the lungs, and especially in the gut. For decades, popular accounts claimed that bacterial cells outnumbered human cells in the body by 10 to 1. More careful estimates published in the 2010s revised the ratio to approximately 1 to 1, with the bacteria slightly more numerous in some people and less in others. The community is not just along for the ride. Gut bacteria help digest food, produce essential vitamins, and train the immune system. Skin bacteria help defend against pathogens. The composition of the microbiome influences digestion, immunity, mental health, body weight, and the risk of various diseases. People with disrupted microbiomes, from antibiotics or illness, often suffer measurable consequences. The community is, in functional terms, an organ. The genetic contribution is striking. The total number of genes in the microbiome is somewhere between 200 and 300 times the number in the human genome. Most of the metabolic activity that keeps a person alive is performed using enzymes encoded not in human DNA, but in the genomes of resident bacteria. From a strict molecular biology perspective, the body is mostly running on borrowed code. The implication is that the boundary between self and not self is less crisp than ordinary language assumes. The cells that make up you, that share your blood supply and respond to your hormones, are a minority of the cells that travel under your skin. The genes that maintain you are mostly bacterial. The thing you call yourself is, more accurately, an ecosystem with a body wrapped around it. The bacteria that share your space are not parasites. They are, by every working definition, a part of you. Gabriel's horn. In the 17th century, the Italian mathematician Evangelista Torricelli described a strange three-dimensional shape now called Gabriel's horn. The shape is formed by rotating the curve of 1 over x between 1 and infinity around the x-axis. The resulting shape looks like a long, thin trumpet stretching out to infinity, narrowing toward but never quite reaching the axis. Mathematically, the shape has a strange combination of properties. Its volume is finite. Its surface area is infinite. The volume can be calculated using ordinary integration. The result comes out to pi cubic units, a finite number. The surface area, calculated by the same standard methods, diverges. The horn, in other words, can be filled with a finite amount of paint, but no amount of paint is enough to coat its outside surface. The result was so counterintuitive that contemporaries called it the painter's paradox. The paradox dissolves when one looks closely at what painting and filling mean. To paint a real surface, you need a layer of paint with some non-zero thickness. As the horn narrows, the layer of paint eventually exceeds the diameter of the horn, so the paint stops covering anything new. To fill the horn with paint, by contrast, you simply pour in liquid that flows into ever narrower regions, the volume converging to a finite limit. The shape is a useful demonstration of how infinity behaves under integration. Some unbounded regions have finite total area or volume, while others do not. The pattern depends on how fast the boundary approaches zero. Gabriel's horn is the borderline case. The volume integral converges while the surface area integral diverges. The combination feels impossible. It is, in fact, a clean result of the calculus that handles such shapes. Superconductivity. In 1911, the Dutch physicist Heike Kamerlingh-Onnes was studying the electrical resistance of mercury at very low temperatures. He found, to his surprise, that below about 4.2 degrees above absolute zero, the resistance dropped to zero. Not very small, exactly zero. An electric current set in motion in a superconducting loop continues to flow indefinitely without any external power source to maintain it. The phenomenon is called superconductivity. A current circulating in a superconducting ring is the closest thing physics knows to a true perpetual motion. Experiments have measured currents persisting for years with no detectable decay. Calculations based on the absence of resistance suggest the currents could continue, in principle, for billions of years before any meaningful loss. The energy stored in the moving electrons is fully conserved. Superconductivity is a quantum mechanical effect. At sufficiently low temperatures, electrons in certain materials pair up into so-called Cooper pairs, which behave as a single coherent quantum state spanning the whole material. The pairs move through the lattice without scattering off impurities or vibrations, the way ordinary electrons do. There is, in effect, no friction at the level of individual electrons, because they have stopped being individuals. Modern applications use the effect in magnetic resonance imaging machines, particle accelerators, and quantum computers. Superconducting magnets produce the strongest steady magnetic fields humans can generate, far stronger than anything possible with ordinary copper coils. Higher temperature superconductors, discovered in 1986, work above the boiling point of liquid nitrogen, making practical applications cheaper. A material capable of sustaining a current that never dies is no longer a laboratory curiosity. It is a working piece of modern technology. Benford's law. If you collect a large number of measurements from many different sources, financial records, populations, river lengths, stock prices, the leading digit of each number follows a strange pattern. About 30% of the numbers will start with the digit 1. About 17% will start with 2. The proportion decreases for each successive digit. Numbers starting with 9 appear less than 5% of the time. The distribution is called Benford's law. The pattern was first noticed in 1881 by the American astronomer Simon Newcomb, who observed that the early pages of logarithm tables, listing numbers starting with 1, were more worn than the later pages. The American physicist Frank Benford rediscovered the pattern in 1938 and showed that it applied to a remarkable range of data sets. The underlying reason involves the scale invariance of many natural processes and the properties of logarithms. The law has practical uses in forensic accounting. Genuine financial data tends to follow the Benford distribution. Fabricated data, generated by humans trying to look random, tends not to. People asked to invent figures will distribute the leading digits more uniformly than the law predicts. By comparing the distribution of leading digits in a financial filing to the Benford expectation, auditors can spot likely fraud with statistical confidence. The Internal Revenue Service in the United States, the Securities and Exchange Commission, and similar bodies in other countries have used Benford analysis in real fraud investigations. The pattern does not prove that any given filing is fake. It does flag filings worth a closer look. A statistical regularity, hidden in plain sight in the leading digits of natural data, has become a working tool in the hunt for cooked books. Frozen time. Near the event horizon of a black hole, general relativity produces another striking time dilation effect. From the perspective of a distant observer, a clock falling toward the horizon ticks more and more slowly the closer it gets. At the horizon itself, in the mathematical limit, the clock appears to freeze. Light from the falling clock becomes increasingly red, shifted and dim, until the image fades into the background. The freezing is only an appearance from outside. The infalling clock, in its own frame, experiences nothing special as it crosses the horizon. Time continues at the normal rate. It falls inward, eventually reaching the singularity at the center, where ordinary general relativity breaks down. The distant observer never sees this happen. From the outside, the falling object hangs suspended at the horizon for all eternity. The result is one of the strangest features of black holes. Two different observers in the same physical system can disagree completely on whether a given event has occurred. The observer falling in says yes, the crossing happened, and the singularity follows. The observer at a distance says no, the crossing has not yet happened, and the object is still very nearly at the horizon. Both views are correct in their own reference frames. The geometry of the situation creates a kind of frozen image of every object that has ever fallen into the black hole. The infalling matter is, from the outside, never quite gone. The black hole's mass and the gravitational pull are real, but the matter contributing to that mass appears, to a distant observer, frozen at the horizon, redshifted into invisibility, suspended in a moment that never quite ends. Non-Newtonian fluid, a mixture of cornstarch and water in the right proportions, produces a substance that behaves differently depending on how it is handled. Sit a spoon in the mixture, and the spoon slowly sinks like in any liquid. Strike the surface sharply, and it feels like hitting a solid wall. The substance is one of the simplest examples of a non-Newtonian fluid, where viscosity depends on the rate of applied stress. In a Newtonian fluid like water, the viscosity is constant regardless of how fast or slow the fluid is sheared. In a shear thickening fluid like the cornstarch mixture, viscosity rises sharply when the fluid is forced to deform quickly. Microscopically, the suspended cornstarch particles are normally lubricated by water between them. When stress is applied rapidly, the particles cannot rearrange fast enough to flow past each other, and they jam into a temporary rigid structure that resists further movement. The behavior has practical applications. Shear thickening fluids are used in some impact-resistant materials, including experimental body armor. The armor stays flexible under ordinary movement and stiffens instantly when struck by a high-velocity projectile. The fluid does the work of converting kinetic energy into a brief solid state, then relaxing back to a liquid afterward. A different type of non-Newtonian behavior shows up in shear thinning fluids, like ketchup or paint, which flow more easily the harder they are stirred. Toothpaste, blood, quicksand, and many polymer solutions all behave non-Newtonianly in one direction or another. The simple categorization of substances as solid, liquid, or gas turns out to be a rough approximation. Many real materials live in an intermediate zone where their behavior depends on context. Blindsight. In rare cases, damage to the primary visual cortex of the brain produces a condition called cortical blindness. The patients report seeing nothing in the affected part of the visual field. They are, by every clinical measure, blind in that region. They walk into objects on the affected side, cannot read text placed there, and report no visual experience whatsoever. Yet careful experiments reveal that some of these patients can still respond to visual stimuli they cannot consciously see. Asked to guess which of several objects is shown in the blind area, they perform far better than chance. Asked to reach for an unseen object, they often reach to roughly the right spot. Confronted with an angry face in the blind field, they show physiological signs of stress. They cannot describe what they have seen, but their behavior reveals that they have processed it. The condition is called blindsight. It works because the visual system has multiple parallel pathways. The primary cortical route is what produces conscious visual experience. Other pathways, through subcortical structures like the superior colliculus, process visual information without producing awareness. When the cortical route is damaged, the other pathways continue to operate. The brain still receives and processes the information. The conscious experience of seeing is what is missing. The implication challenges naive ideas about vision. Conscious sight and visual processing are not the same thing. A person can be functionally blind in the sense that they have no visual experience, while still having a brain that registers shapes, faces, motion, and emotional content. The connection between seeing and conscious awareness, which feels seamless from the inside, turns out to be a separable structure. The brain can show the world to itself without ever telling its owner. Cosmic horizon. The observable universe is bounded by a horizon. Light travels at a fixed speed, and the universe has a finite age. Light from objects more than about 46 billion light-years away has not had time to reach us. Anything beyond that boundary is, in a strict observational sense, invisible. We can never see it. The galaxies in that region are real, in any reasonable physical sense, but their light has not arrived. The horizon is also expanding, but more slowly than the universe itself. As space stretches, galaxies that are close to the current horizon are being pushed outward by the expansion of space. Some of them, far enough away, are receding faster than light can cross the gap. Light they emit today will never reach us. Each such galaxy crosses the horizon and disappears from the observable universe forever. Modern measurements of dark energy show that the expansion is accelerating. The cosmic horizon is therefore shrinking over time, in the sense that less and less of the universe will remain observable. Over the next 100 billion years or so, almost all galaxies outside our own local group will recede past the horizon. They will not, in any real sense, vanish. They will simply pass beyond the reach of any future telescope, never to be seen again. The implication is that the observable universe of the deep future will look very different. A civilization living in the merged remains of the Milky Way and Andromeda 100 billion years from now will see only their own galaxy and a few small companions. The rest of the cosmos will have receded into invisibility. Without external galaxies to observe, they will have no way of knowing that the universe is expanding. 0.999 equals 1. The decimal 0.9999, with the nines repeating forever, is exactly equal to 1. Not approximately equal, not arbitrarily close, equal. The result follows from the standard definitions used in modern mathematics. Despite being a settled fact, it remains one of the most contested results in popular mathematical discourse, with countless internet arguments and bewildered students every year. The simplest proof uses elementary algebra. Let x equal 0.999 repeating. Multiply both sides by 10 to get 10, x equals 9.999 repeating. Subtract x from 10x. On the left, you get 9x. On the right, you get 9, because the infinite trailing 9s on each side cancel. So 9x equals 9, which means x equals 1. The decimal 0.999 repeating was, all along, just another name for the number 1. A second proof uses limits directly. The repeating decimal is, by definition, the sum of an infinite series. Each successive 9 adds another decreasing power of 10. The total approaches, but never quite reaches 1, in the language of finite arithmetic. The standard definition of an infinite decimal, however, is the limit of the series, not any partial sum. The limit of the partial sums is exactly 1. The decimal evaluates to that limit. The result is a clean illustration of how mathematics handles infinity. Two different decimal expansions can represent the same number, because the operation of writing a number in decimal form has a small ambiguity at certain values. The number is the same. The notation has multiple forms. Once the formal definitions are accepted, the equality is unavoidable. The fact that intuition resists it is a sign that intuition was not built for handling infinite expansions. Quantum photosynthesis. Photosynthesis is the process by which plants and certain bacteria capture energy from sunlight. A photon strikes a chlorophyll molecule in the chloroplast of a plant cell. The energy is then transferred through a network of pigments to a reaction center, where it drives a chemical reaction that ultimately stores the energy in sugar. The transfer between pigments is fast, taking only a few picoseconds, and remarkably efficient. The efficiency was a puzzle for decades. The energy could in principle be lost as heat, fluorescence, or various wrong path-side reactions. In practice, plants capture nearly all the energy that reaches the reaction center. Recent experiments have shown that the secret lies in quantum coherence. The energy does not hop from pigment to pigment by classical diffusion. It explores multiple paths simultaneously, in a quantum superposition, and arrives at the reaction center by the most efficient route. The result was confirmed in 2007 by experiments on the green sulfur bacterium using ultra-fast spectroscopy. The team showed that quantum coherence persists in the photosynthetic apparatus for surprisingly long times, even at room temperature in a warm, wet biological environment. The conditions were thought to be hostile to quantum effects. The protein structure around the pigments appears to protect the coherence long enough for it to matter. The implication is that plant biology is, at its core, using quantum mechanics to do its work. The energy capture system that supports almost all life on Earth is not a classical machine. It is a quantum machine, optimized by billions of years of evolution to exploit superposition and coherence in ways that human engineering is only beginning to understand. Every breath of oxygen you take comes from a process that, at the smallest scales, runs on quantum tricks. Cosmic motion. The chair you are sitting in feels solid and still. The earth beneath it feels equally still. The reality is otherwise. The earth rotates on its own axis at about 1,000 miles per hour at the equator. At the same time, the Earth is orbiting the Sun at roughly 67,000 miles per hour. The Sun, in turn, is orbiting the center of the Milky Way galaxy at about 500,000 miles per hour. The galaxy itself is moving. The Milky Way is falling toward the Andromeda galaxy at over 200,000 miles per hour, on the long path to a future collision. The local group of galaxies is being pulled toward a large galaxy cluster called the Virgo cluster. The whole local supercluster is moving toward an even larger structure called the Great Attractor, hidden in the direction of the constellation Centaurus. When all these motions are added up, the planet you are standing on is hurtling through space at roughly 1 million miles per hour, relative to the average rest frame of the cosmic microwave background. Every second, you move about 300 miles further along that trajectory. You will not, of course, ever return to the spot you occupy now. By the time you finish reading this paragraph, you are tens of thousands of kilometers away from where you started. The reason you do not feel any of this is that the motion is smooth and unaccelerated in the local frame. Only changes in velocity, not velocity itself, produce a felt force. Galileo pointed this out 400 years ago in his discussion of relativity. The chair, the room, the earth, and you are all moving together at the same enormous speed. The shared motion is invisible from the inside. The cosmos, however, has the receipts. Expanding ice. Water is one of the few substances that becomes less dense when it freezes. Most materials contract as they cool, becoming denser in the solid phase than in the liquid. Water reverses this near its freezing point. As it cools below 4 degrees Celsius, it begins to expand again, and when it crystallizes into ice, the expansion produces a solid that is less dense than liquid water. The result is that ice floats. The anomaly is a consequence of the water molecule's specific shape. 2 hydrogen atoms attached to 1 oxygen with a bent geometry and partial electric charges give the molecule a strong tendency to form hydrogen bonds with its neighbors. In liquid water, these bonds form and break constantly, allowing dense packing on average. In ice, the bonds lock into an open hexagonal lattice that holds molecules further apart than they were in the liquid. The lattice is rigid but spacious. The consequences are enormous. When a pond or lake freezes in winter, the ice forms on top instead of at the bottom. The frozen layer insulates the liquid below, allowing aquatic life to survive through the cold months. Without this anomaly, lakes would freeze from the bottom up, and most temperate and polar aquatic ecosystems could not exist. Many fish, amphibians, and microorganisms depend on the floating ice as a thermal blanket. The same expansion does damage when water freezes inside pipes, rocks, or biological tissue. Frozen pipes burst. Frost weathering breaks rocks. Frostbite tears cells apart from the inside. The very property that makes liquid water unusually friendly to life also makes solid water unusually destructive. Life as we know it has evolved to exploit one face of the anomaly and protect itself from the other. Quantum superposition. A particle in quantum mechanics does not have a single definite position until it is measured. Instead, it exists in a superposition of multiple possible positions at once. The superposition is described by a wave function that spreads through space, with the square of the wave function giving the probability of finding the particle at any particular location. Until the measurement is made, the particle is, in a strict mathematical sense, at all of its possible locations simultaneously. This is not a statement about ignorance. It is not that the particle is at one of the positions, and we simply do not know which one. Experiments designed to distinguish these two interpretations consistently show that the particle is in a real superposition. The two-slit experiment, for example, only produces interference if each particle passes through both slits in some quantum mechanical sense. Treating the particle as having a single hidden position fails to predict the data. The superposition extends to other properties as well. A particle can be in a superposition of different spins, different momenta, different energies. The size of the system that can be put into a superposition has steadily grown. Originally limited to individual photons and electrons, modern experiments have created superpositions of large molecules, including molecules of more than 2,000 atoms. The Schrödinger cat thought experiment is steadily being approached by real laboratories. The implication challenges everyday notions about what it means for an object to exist. Quantum systems do not have definite properties until measured. The world at small scales is genuinely indeterminate in this technical sense. The reason ordinary objects appear to have definite properties is that they constantly interact with their environment, which acts as a continuous measurement that destroys superpositions before they grow. The strangeness is hidden by the busy world. Vacuum energy. In 1948, the Dutch physicist Hendrik Casimir predicted a small but measurable force between two uncharged conducting plates placed very close together in a vacuum. The prediction was a direct consequence of quantum field theory. The vacuum is filled with virtual particles flickering in and out of existence. Between the plates, only certain wavelengths of these virtual particles can fit. Outside the plates, all wavelengths are allowed. The imbalance produces a net inward pressure that pushes the plates together. The Casimir effect was first directly measured in 1997, with great precision matching the predictions. The force is small at human scales. Between plates a few micrometers apart, the pressure is around 1 atmosphere. At larger distances, the force falls off rapidly. At very small distances, it grows large enough to affect the design of microelectromechanical systems and other precision devices. The effect proves that the energy of the vacuum is not zero. Empty space contains a residual zero-point energy that can do work on objects placed within it. The plates can be made to come together, slowly, with the vacuum providing the energy. In principle, this energy could be extracted, although the amount per use is small and the engineering required to scale it up may be impossible. The result is one of the most direct experimental confirmations that the vacuum, far from being nothing, is a dense and active medium. It also raises one of the deepest puzzles in physics. When physicists try to calculate the total energy density of the vacuum, the answer they get is enormously larger than what observations of the universe allow. The mismatch, called the cosmological constant problem, is one of the largest unresolved discrepancies in all of science. Uncomputable problems. In 1936, the British mathematician Alan Turing proved that there are mathematical problems no computer can ever solve. The specific problem he considered is now called the halting problem. Given the description of any computer program and an input, no general algorithm can decide whether the program will eventually halt or will run forever. Turing showed that no such algorithm exists. The question, in full generality, is undecidable. The proof uses a self-referential construction similar to Gödel's. Assume a hypothetical algorithm exists that solves the halting problem. Build a new program that uses this algorithm to predict its own behavior and then does the opposite. The predicted halt becomes a non-halt and vice versa. The contradiction shows that the original assumption was wrong. No algorithm can decide the halting problem for all possible inputs. The result has wide-reaching consequences. Many other questions about programs and mathematical structures turn out to be reducible to the halting problem. Whether a given program is correct, whether two programs compute the same function, whether a piece of code contains certain bugs. All of these are, in general, undecidable. There is no algorithm that, given any program, can always determine whether it has any of these properties. Practical computer science has learned to work around the limit. For specific kinds of programs, in specific kinds of analysis, halting can often be decided. Verification tools, type checkers, and program analyzers all rely on practical approximations to the undecidable problem. The deeper point survives. There are well-defined questions about computation that no computer, however powerful, can ever answer. The limits of mechanical reasoning, like the limits of mathematical proof, are not a matter of engineering. Monty Hall, in a classic puzzle, a game show contestant is shown 3 closed doors. Behind one door is a car. Behind each of the other 2 is a goat. The contestant picks a door. The host, who knows where the car is, opens one of the other 2 doors to reveal a goat. The contestant is then offered the choice to stick with the original door or switch to the remaining unopened door. The question is whether switching improves the contestant's odds. The intuitive answer, given by most people on first encounter, is no. 2 doors remain, one with a car and one with a goat, so the odds appear to be 50-50. Switching should not matter. The intuitive answer is wrong. Switching doubles the probability of winning the car from 1/3 to 2/3. Sticking with the original door wins 1/3 of the time. The reason is that the host's action provides information. The probability that the contestant's initial guess was correct is 1 in 3. The probability that the car is behind one of the other 2 doors is 2 in 3. By opening one of those 2 doors and showing a goat, the host has concentrated the entire 2/3 probability onto the single remaining unopened door. Switching captures that concentration. Staying does not. The puzzle, popularized in the 1990s by the Parade magazine columnist Marilyn Vos-Savant, produced enormous controversy. Even professional mathematicians wrote in to dispute her correct answer. Simulations and careful arguments eventually convinced almost everyone. The Monty Hall problem has since become a standard example of how intuition fails in conditional probability. The arithmetic is unambiguous. The intuitive resistance is the lesson. Aperiodic tiling, a normal tile pattern, like the one on a bathroom floor, repeats. Slide the pattern by some specific distance, and it lines up exactly with itself. Mathematicians proved early in the 20th century that any periodic tiling of the plane must use shapes whose symmetries are compatible with the basic group of patterns. 5-fold symmetry, the kind seen in pentagons and pentagrams, was thought to be impossible in a tiling that covered an infinite plane without gaps. In 1974, the British mathematical physicist Roger Penrose discovered tilings that violated this expectation. Using just 2 simple shapes, sometimes described as kites and darts, he produced patterns that cover the plane completely, with no gaps and no overlaps, and never repeat. Slide a Penrose tiling by any distance in any direction, and it does not match itself. The pattern has long-range order, but no periodicity. The Penrose pattern has surprising properties. It contains 5-fold symmetry, which was thought to be incompatible with infinite tiling. The ratio of the 2 types of tile in any large enough region of the pattern approaches the golden ratio. The tiles can be assembled in many different ways, but careful matching rules ensure that every resulting tiling has the same statistical properties. The order is hidden, but real. A startling sequel arrived in 1982. The Israeli materials scientist Dan Shechtman discovered a real metal alloy whose atomic structure showed exactly the kind of five-fold symmetry Penrose had drawn on paper. The new state of matter was called a quasi-crystal. Shechtman was dismissed by colleagues for years until the structure was confirmed and theoretically understood. He received the Nobel Prize in Chemistry in 2011. The mathematical curiosity turned out to be a real way for atoms to arrange themselves. Cherenkov radiation. When a particle travels through a medium faster than light travels through that same medium, it produces a faint blue glow called Cherenkov radiation. The effect is real, observable, and visible in the cooling pools of working nuclear reactors. The water surrounding a reactor core glows a soft blue. The glow is produced by electrons emitted during fission, moving through the water at speeds higher than the local speed of light in water. The basic rule that nothing can exceed the speed of light applies only in a vacuum. In other materials, light slows down. In water, the speed of light is about 3/4 of its vacuum value. Energetic particles, which are not slowed by the medium in the same way, can therefore exceed the local light speed without violating relativity. The vacuum speed limit is intact. The medium's slower light is what gets overtaken. The physical mechanism is analogous to a sonic boom. A supersonic aircraft moves faster than sound waves in air can propagate, producing a cone of compression that arrives as a boom. A superluminal charged particle in a medium produces a coherent electromagnetic shock wave, which appears as Cherenkov radiation. The angle of the emission cone, the wavelength distribution, and the color are all predicted by the same wave mechanics. The blue color is not accidental. Cherenkov radiation is emitted more strongly at shorter wavelengths, which puts the peak in the blue and ultraviolet. Detectors based on the effect are used in particle physics experiments to identify the speed and type of charged particles passing through transparent media. The same glow that warns people not to swim near a reactor pool is, in instrumented form, one of the standard tools of high-energy physics. Relative simultaneity. In Einstein's special relativity, the notion of two events happening at the same time is not absolute. Two events that appear simultaneous to one observer may appear sequential to another, with the order between them depending on the relative motion of the observers. The effect is called the relativity of simultaneity, and it is one of the most counterintuitive consequences of relativity. The classic example involves a train and a station. Lightning strikes both ends of a moving train in such a way that an observer on the station platform sees both strikes simultaneously. The observer is exactly in the middle of the two impacts, and the light reaches them at the same time. An observer in the middle of the train, however, is moving toward the front of the train relative to the platform. Light from the front strike reaches them slightly before light from the rear. To them, the front strike happened first. Both observers are right, in their own frames of reference. There is no absolute fact about which strike came first. The temporal order of distant events depends on who is asking. The result destroys the everyday notion of a single shared present moment. Your now and a stranger's now, separated by some distance and moving at different velocities, are literally not the same instant. The effect is small at human walking speeds, but real. For events separated by larger distances or higher speeds, the disagreements grow. At cosmological scales, what counts as the present in our galaxy can correspond to the deep past or far future in another galaxy moving differently. The concept of a single, universal present moment, which feels intuitively obvious, turns out to be a parochial human assumption that the universe does not honor. Frame dragging. Einstein's general relativity predicts that a rotating massive body drags the surrounding space and time along with it, in the same direction as its rotation. The effect is called frame dragging, or the lens-Thirring effect. Space, in this picture, is not a passive backdrop. It is a dynamic medium that responds to the motion of matter, including being twisted by a spinning mass. The effect is small in ordinary conditions. Around the Earth, frame dragging tilts the orbits of low-altitude satellites by a tiny but measurable amount. The Gravity Probe B mission, launched in 2004, confirmed the predicted effect to high precision. The satellite carried 4 extremely precise gyroscopes that, over the course of the mission, slowly twisted in the direction predicted by frame dragging from the rotating Earth below. The effect is much stronger around rapidly rotating compact objects. Near a spinning black hole, space is dragged so strongly that no observer can remain stationary near the horizon. The region where this happens is called the ergosphere. Inside the ergosphere, even an object with the most powerful imaginable engines cannot stand still relative to a distant observer. The local space itself is rotating, and everything in it is forced to rotate too. The implication overturns the everyday assumption that space provides a neutral arena for events. Space is part of the system. Mass and rotation can shape it, twist it, and carry it along. The familiar geometry of 3 perpendicular dimensions plus time is, in general relativity, a low-energy approximation. The full theory describes a fabric that bends, expands, and gets dragged along by massive things in motion. Supercooled water. Ordinary water freezes at 0 degrees Celsius. The freezing requires a nucleation site, usually a piece of dust or a rough surface, for the first ice crystal to form. In very pure water held in a smooth container, no nucleation site is available, and the water can be cooled well below its freezing point while remaining liquid. The supercooled state is fragile. A single disturbance can trigger immediate crystallization throughout the volume. Carefully prepared supercooled water has been brought down to about -40 degrees Celsius before homogeneous nucleation kicks in spontaneously. The effect is responsible for the way bottles of soda or beer can be retrieved from a freezer, apparently liquid, only to freeze solid the moment they are opened or tapped. The shock provides the missing nucleation site, and the cascade of ice formation runs through the bottle in seconds. Supercooled water plays a role in real atmospheric processes. Cloud droplets often exist as supercooled water below freezing temperatures, held liquid by the absence of suitable nucleation sites. When such a droplet hits an aircraft wing, the impact triggers freezing, producing the dangerous ice buildup pilots call rime. Cloud seeding, used in some weather modification programs, works by providing artificial nucleation sites to trigger precipitation from clouds full of supercooled water. The deeper point is that the phase boundary between liquid and solid is not a single well-defined temperature. The familiar 0 degrees Celsius freezing point is only the threshold where freezing becomes thermodynamically favored. Whether and when it actually happens depends on kinetics, the availability of nucleation sites, and the history of the sample. Water is a more complicated substance than the simple phase diagram suggests. Bose-Einstein condensate. In 1924, the Indian physicist Satyendra Nath Bose and Albert Einstein predicted a new state of matter that would appear at extremely cold temperatures. At temperatures very close to absolute zero, a large number of certain kinds of atoms could merge into a single quantum state. all behaving as one entity. The predicted state is now called a Bose-Einstein condensate. The state requires temperatures within a millionth of a degree of absolute zero. For 7 decades after the prediction, no laboratory could achieve such conditions. In 1995, the American physicists Eric Cornell and Carl Wieman, along with Wolfgang Ketteler, finally produced the first Bose-Einstein condensate using rubidium atoms cooled by laser and evaporative cooling. The achievement won the Nobel Prize in Physics in 2001. The condensate is a strange object. Millions of atoms occupy a single quantum state, all described by the same wave function. They lose their individual identities. The cloud of atoms behaves as one quantum object, moving and interacting with the world as a single coherent entity. Light passing through the condensate can be slowed to walking speeds. Coherent matter waves of the condensate can interfere with one another, similar to overlapping light waves. The result is one of the clearest examples of quantum mechanics operating at a scale visible to the naked eye. The condensate is typically 100 micrometers or so across, large enough to be photographed. Modern research uses condensates to model superconductivity, superfluidity, and a wide range of quantum many-body effects. The state was once a theoretical curiosity. It is now a working laboratory tool for studying the most counterintuitive aspects of quantum mechanics, where many particles behave as one. Olbers Paradox. In an infinite, eternal, and roughly uniform universe filled with stars, every line of sight from the Earth should eventually hit a star. The sky should be uniformly bright in every direction, day and night, blazing with the combined glow of stars at every distance. The night sky should be as bright as the surface of the sun. The fact that it is not, that the night sky is overwhelmingly dark, is called Olbers Paradox. The paradox was discussed for centuries. The German astronomer Heinrich Olbers laid out the problem in 1823, building on earlier observations by Kepler and others. Various proposed resolutions failed under scrutiny. Dust between stars could absorb light, but it would then heat up and re-emit the energy, eventually contributing to the same uniform glow. The puzzle survived as a deep problem in cosmology for over a century. The modern resolution comes from the finite age of the universe. The cosmos is about 13.8 billion years old. Stars in distant galaxies emit light that, even traveling at the speed of light, takes billions of years to reach Earth. Only stars within a sphere of around 13 billion light-years can contribute to the night sky here. Beyond that distance, light has not yet had time to arrive. The number of contributing stars is enormous but finite. The expansion of the universe also helps. Light from distant galaxies is stretched into longer wavelengths, reducing its energy and brightness. Combined with the finite age of the universe, this leaves the night sky genuinely dark in the visible spectrum. The faint glow of the cosmic microwave background is, in a sense, the brightness Olbers expected, redshifted into the microwave range. The night sky is not bright because the universe is not old enough to fill it up. Quantum eraser, a variation of the double-slit experiment, called the quantum eraser, takes the strangeness further. Set up the experiment so that each particle is marked, as it passes through the slits, with information about which slit it took. Marking destroys the interference pattern. Then add a second component that, after the particles have already arrived at the detector, erases the path information. When the information is erased, the interference pattern returns in the subset of particles whose information was erased. The result is unsettling. The decision to erase or preserve the path information is made after the particle has already arrived. Yet the pattern observed for those particles depends on whether the erasure was done. Erase the information, and they show the wave-like pattern. Preserve it, and they show the particle-like pattern. The behavior appears to depend on a choice made after the fact. Experiments performed since the late 1990s confirm the predicted result. No information is being sent backward in time. The pattern only becomes visible when the experimenter sorts the data according to which group each particle belonged to. The full unsorted data shows no interference. The interference appears only after the sorting. The strangeness lives in the correlation between which path information and the arrival pattern, not in any direct backward causation. The deeper lesson is that quantum mechanics does not allow particles to have well-defined classical histories. The wave function describes a distribution of possible histories that only resolves when information is recorded somewhere in the world. Erasing the recorded information lets the alternatives re-interfere. The choice the experimenter makes determines what the data eventually shows. The world, at quantum scales, does not commit to a single story until the recording is complete. Collatz conjecture: take any positive whole number. If it is even, divide it by 2. If it is odd, multiply it by 3 and add 1. Apply the same rule to the result and keep going. The conjecture, posed by the German mathematician Lothar Collatz in 1937, claims that every starting number eventually reaches 1. After enough steps, the sequence enters the loop 4, 2, 1 and stays there. The pattern is easy to test. Try 14. 14 is even, so divide by 2 to get 7. 7 is odd, so multiply by 3 and add 1 to get 22. 22 becomes 11, then 34, then 17, then 52, 26, 13, 40, 20, 10, 5, 16, 8, 4, 2, 1. The path is irregular, climbs and falls unpredictably, but always reaches 1. Computers have verified the conjecture for every integer up to enormous values, far beyond what any human can check by hand. No one has proved that it works for every integer. The conjecture is famously simple to state and famously unsolved. Generations of mathematicians have tried. Some of the most accomplished number theorists, including Paul Erdos, openly stated they did not know how to attack it. Erdos said mathematics was not yet ready for such problems. Modern partial results show that almost all integers eventually reach a small value, but the full conjecture remains open. The puzzle is a reminder that simplicity in statement does not imply simplicity in proof. A rule a third grader can apply produces a problem the entire mathematical community has failed to crack. The number theory hidden inside the Collatz sequence is, in some not understood sense, deep enough to resist every available technique. The numbers obey the rule. Whether they always reach one is a question still open. Tetrachromatic vision. Most humans are trichromats. The retina contains 3 types of cone cells, each sensitive to a different range of wavelengths. The brain combines signals from the 3 cones into the perception of millions of colors. A small minority of women, due to a quirk of the X chromosome and the genes for cone pigments, carry the genetic makeup for a 4th cone type. In rare cases, the extra cone is functional and the woman perceives the world as a tetrachromat. True functional tetrachromats are extremely rare. Researchers in the United Kingdom and the United States have identified a small number of women whose color perception, tested with careful psychophysical methods, exceeds the range of ordinary trichromacy. They can distinguish colors that look identical to everyone else. They can sort colored chips into more groups than 3 cone vision permits. They are seeing more. The number of additional colors a tetrachromat can perceive depends on the spectral properties of the 4th cone. In principle, the additional dimension of color perception multiplies the number of distinguishable colors by a factor of around 100. A trichromat distinguishes around 1 million colors. A tetrachromat may distinguish 100 million. The world looks the same. The color names are the same. The distinctions a tetrachromat perceives are mostly impossible to describe to a trichromat. The implication is that the color space accessible to human perception is wider than most people realize. The color palette you take for granted is not a complete inventory of what eyes can see. It is the version available to a typical trichromat. For a small number of people, the world is genuinely more colorful in ways that ordinary language and ordinary screens cannot represent. The extra colors exist. Most people never see them. Spaghettification. A person falling into a black hole experiences something more violent than freezing time. Tidal forces, the difference in gravitational pull on different parts of an object, grow enormous near a black hole. For a stellar mass black hole, the gravity at the feet of a falling person is so much stronger than at the head that the body is stretched into a long, thin thread of matter. The effect is known, with characteristically dry physicist humor, as spaghettification. The stretching happens before the person reaches the event horizon. The smaller the black hole, the more violent the tidal forces near it. For a black hole a few times the mass of the Sun, spaghettification begins thousands of kilometers outside the horizon and quickly tears the falling object apart at the molecular level. The atoms of the body are pulled into a long stream that spirals into the hole. For a supermassive black hole, the kind found at the centers of galaxies, the geometry is different. The horizon is much larger, the tidal forces are correspondingly smaller, and a person could in principle cross the horizon without being noticeably stretched. Once inside, however, the same fate awaits. The spaghettification simply happens deeper in. Eventually, the falling matter reaches a region where the tidal stretch overwhelms any chemical bonds, and the body is reduced to a thread. The fate of the matter beyond that point is not well understood. General relativity predicts a singularity at the center, where curvature becomes infinite and the laws of physics break down. Some form of quantum gravity is expected to govern the final fate. Whatever it is, the matter that fell in has been first stretched into a string and then driven toward a destination no known theory can describe. Change blindness. In a classic experiment, 2 photographs of the same scene are shown in sequence on a screen, separated by a brief flash of blank. The 2 photographs differ in some way. A door has appeared, a person has changed places, an object has been removed. The change is large and obvious. Yet viewers, asked to compare the photos, often fail to notice the change for an extraordinarily long time. The phenomenon is called change blindness. Change blindness exposes a gap between the rich, detailed visual experience people feel they have and the much sparser representation the brain actually maintains. When you look at a scene, you have the impression of seeing everything in it at once. In fact, you have a clear image only near the point of fixation. The rest is filled in by memory, expectation, and assumptions about visual continuity. As long as the brain expects the scene to remain stable, it does not actively check. A brief interruption defeats the system. The blank flash, or a saccade, or even a small mask that hides the change as it occurs, breaks the motion-based signal that would normally alert the brain to the alteration. Without that signal, the the brain compares its assumptions to the new image and, often, fails to spot any difference. In real-world experiments, people have failed to notice when an experimenter handing them a clipboard was replaced by a different person mid-conversation behind a passing door. The implication is that ordinary visual perception is not a continuous high-resolution recording of the world. It is a sketch, supplemented by rapid lookups and assumptions. The richness you experience is a confabulation, not a stream. Most of the time, the assumptions match reality closely enough to be useful. When they do not, large changes can occur in plain sight and go unnoticed. The illusion of seeing it all is, on close inspection, an illusion. Observable Universe. The universe is about 13.8 billion years old. Common sense suggests that the visible universe should therefore be a sphere about 13.8 billion light-years in radius. The distance light has had time to travel. Common sense is wrong. The observable universe is about 93 billion light-years in diameter, far larger than the simple light travel calculation would allow. The difference comes from the expansion of space itself. When ancient light from a distant galaxy was first emitted, the galaxy was relatively close. Over the billions of years the light traveled toward us. The space between us and the galaxy stretched. The galaxy moved further away while the light was in flight. By the time the light arrives at our telescopes, the galaxy that emitted it is now far more distant than it was when the light left. The current distance to the most distant visible galaxies is about 46 billion light-years. The light still took 13.8 billion years to make the trip, because both space and the light were in transit at once. The total radius of the observable universe is the present distance to objects whose ancient light is just now arriving. That distance has grown with the expansion. The visible universe is bigger than the speed of light times its age, because space did not stay the size it was when the photons started traveling. The result feels paradoxical. Nothing moves faster than light, yet the universe contains observable structure at distances that simple speed of light arithmetic would forbid. The trick is in the geometry. The expansion of space is not a velocity through space. It is a stretching of the underlying coordinates. The light that fills your sky tonight has been carried over its long journey into a sphere larger than the naive picture allows. Stopped clock illusion. When you glance from one place to another, and your eyes happen to land on a clock with a second hand, the first tick of the second hand often seems to last too long. The second hand appears frozen for a moment before resuming its normal rate. The illusion is real and reproducible. It is called chronostasis, and it occurs because of how the brain handles time during eye movements. When you make a saccade, the rapid jump from one fixation to another, your eyes move at hundreds of degrees per second. The visual input during the saccade is a useless blur. The brain handles this by suppressing visual processing during the movement and filling in the gap with what it sees right after the saccade ends. Whatever your eyes land on first is back projected, in time, to fill the perceptual hole the saccade produced. The trick is normally invisible. Most things you look at do not change in any detectable way over the duration of a saccade, around 200 milliseconds. When the target of the saccade is a clock with a moving second hand, the trick becomes visible. The brain projects the post-saccade view backward by the duration of the saccade. The first tick of the second hand therefore seems to take longer than the rest. The clock has been hiding its motion behind your moving eyes. The effect is one of the cleanest demonstrations that the brain edits the timing of perception. Time does not flow into consciousness smoothly. It is constructed with chunks chopped out during saccades and stitched back in with edits to the timeline. Most of the time, the editing matches reality closely enough to be invisible. When the target is a moving clock, the seam shows. Your visual now is, in a strict technical sense, a curated assembly. Second brain. In addition to the brain in your skull, you have a second nervous system running through your digestive tract. The enteric nervous system contains roughly 500 million neurons, more than the spinal cord. It runs as a mesh through the walls of the stomach and intestines, controlling digestion, motility, blood flow, and many other functions without consulting the brain at all. The system is not a remote branch of the central nervous system. It uses its own neurotransmitters, including most of the body's serotonin, which is produced largely in the gut rather than in the brain. It can operate independently when the connections to the brain are cut. The complex coordination of muscles, secretions, and blood vessels that handles each meal is in large part run from the gut itself. The brain in your head receives reports, but does not micromanage the process. The two nervous systems communicate constantly through the vagus nerve and circulating chemicals. The communication is not one way. The gut sends as many signals to the brain as the brain sends to the gut. Disruptions in the gut microbiome and the enteric nervous system have been linked to mood disorders, anxiety, and certain neurodegenerative diseases. The colloquial sense of a gut feeling has a literal anatomical basis. The implication is that you are run by more than one cognitive structure. The skull brain handles consciousness, vision, planning, and language. The gut brain handles digestion, immunity, and a substantial fraction of emotional signaling, mostly outside conscious awareness. The two are coordinated but distinct. Much of what feels like a unified mental life is actually the result of two semi-independent nervous systems negotiating with each other through the central nervous system. Cold ending. The universe is moving toward a state called maximum entropy. Every process that converts energy from one form to another produces some waste heat, spreading energy out into ever more uniform distributions. Stars burn through their fuel, planets cool, structures dissipate. Over enormous timescales, all the available energy gradients are exhausted. The universe ends in a state called heat death. The name is misleading. Heat death does not mean the cosmos heats up. It means the cosmos becomes uniformly cold. Every region eventually settles into the same low temperature, the same density of dilute particles, the same lack of structure. There are no gradients to drive any process. No event can occur, because every part of the universe is in equilibrium with every other part. The clock of the cosmos runs out of fuel. The timescale is so long that even the previous endings on a list of cosmic finalities are brief by comparison. After the last stars burn out, after the last black holes evaporate, after the last protons decay, the universe will continue to expand. The remaining photons and neutrinos will spread out further. The temperature will approach absolute zero, but never quite reach it. The wavelengths of the surviving particles will grow longer than the distances between them. The final state, if it is reached, is the last possible event in the history of the cosmos. After it, time itself becomes featureless. There is no future in any meaningful sense, because no future event distinguishes itself from the present. The arrow of time, which has organized every moment from the Big Bang onward, runs out of direction. Atoms, in the deep future, quietly fall apart. The universe ends not in a bang, but in a uniform, perfectly cold, perfectly silent sea of almost nothing.